Hi everybody, my name is Puya Tabassian and this is another session of DataMine's webinar. Thanks for joining us today. Before we begin, there are just a few things to mention. To view the presentation, you must follow the link provided in the webinar confirmation email from DataMine. Dial-in information is also included within that same email. We have muted the phone lines to prevent background noise, so if you have any questions, please type them into the chat box on your screen. We have allocated time after the formal presentation for our presenters to answer your questions. Joining us today from DataMine Sudbury office is Mr. Damien Gregory. Damien is a senior engineer and has been with the company for 9 years now. Today, he will be showing us new features of our strategic open pit planning application, NPV Scheduler. Mr. Damien, the floor is yours. Please go ahead.
Thanks, Puya. Hello, everyone. Today, I will focus on the functions that we have added in the last two releases of NPV Scheduler. But for the sake of clarity, and because some of you may not be quite familiar with NPV Scheduler, I will provide a brief overview of its functions as well. We all know that providing strategic life of mine plan is a very complex exercise. And the complexity comes from numerous challenges that we need to deal with, like the geological realities, the economic conditions of mining, with their uncertainties, and numerous engineering constraints that we need to consider. Luckily, we have applications like NPV Scheduler that will help us create quality schedules in a very short time. Here we see the flow chart of the process that engineers usually go through to generate a strategic schedule. We started with data importation, we're importing a resource model, we're importing digital terrain models like pushback design. We import additional boundaries that we can use for controlling our pits and pushbacks. We define economic settings to determine the block value for each of the subcells in our resource model. Using this block value, we are utilizing the large Boltzmann algorithm to generate the ultimate pit and divested LG shells. As a result, we see the report of each LG shell that we can continue. Next stage, generating pushbacks. We are defining the inputs, and as a result, we create a series of optimized pushbacks that later we can schedule. The scheduler allows using pushbacks generated within NPV Scheduler, or also we can import pushbacks designed in another general mining package if they can be scheduled. This also includes haulage optimization. Once we have a schedule, we can carry out material allocation or mine flow optimization to evaluate how we can utilize stockpiles to enhance, to increase the NPV of the project and investigate different cut-and-grade strategies. We start with data import. We can import models from different file formats. And at this stage, the users can select the fields available within the resource model and how they need to be used within the application. At the end, we see a brief summary of the content of the resource model to ensure we are importing the correct data fields and we're dealing with the correct resource model before we go to the next stage to define the economic settings. We have a comprehensive tool of defining different prices of our commodities, mining recoveries, processing recoveries, processing costs for each unit of material processed or each unit of metal or product recovered. We can apply rehabilitation costs. We can apply also additional mining costs for each bench As a result, the application is computing the block value, the money cost, processing cost, recoveries for each of the subcells, and it selects which of the possible destinations is the one that will provide the highest net revenue, and this is the destination that will be used in the subsequent stages. At the end of the process, we can see a detailed report about the contents of each elevation within our resource model, and once the block values are computed, we can go to the next stage of generating the ultimate bit. The new functions that we have added in the last releases is the ability to define a particular type of processing methods, such that can upgrade the quality of the material content within the subcell. With the conventional processing methods, they are designed to compute what is the cost, what is the recovered metal for each of the products, what is the processing cost, the downstream cost, to compute the net value. But with this special processing method that you can see here, it allows to change the grade based on the definition defined by the user. In this example, I have only 82% of our input or material will be considered as material available for processing. That means the remaining 18% will be waste reject. This waste is generated because we can change the grades of our products or the various elements. For example, we have here a formula which expresses how my silica grade will be changed if the material goes to this special processing plant. In this case, my silica grade is decreasing using the formula, and in the formula expression you see this the original grade, which is multiplied by 40%, and then we are subtracting 0.028. And this will be the grade of this 82% of material that will be available for the subsequent steps in the process. This option allows us to recover a lot more material, and only this material that will not have sufficient value to be sent to the conventional processing method. Usually the conventional methods have lower cost, but with this upgrading option, we can recover significantly larger part of the deposit. The ultimate bit is generated using the large Gaussian algorithm based on the design slopes that are defined for different geotechnical regions, and it's creating optionally nested LG shells that are providing opportunity to see how we should go about extracting our deposit, where is the most valuable part, where we have to focus our attention first. And these nested LG shells are being used later to generate the optimal extraction sequence from the ultimate pit, which is being used when generating pushbacks. When creating the ultimate pit, we can optionally use polygons. We can assign cost to these polygons, and they can control the shape of the pit and the shape of the nested LG shells. This type of costs are directly impacting the sequence, and they will be used in all subsequent optimization stages. After we create the nested LG shells, we're defining constraints like minimum mass, minimum mining width, to generate practical pushbacks. Pushbacks stages or phases need to honor certain engineering constraints, and they have to be based on the nested LG shells in order to preserve the maximum value. At the end of the process, we presented a report which is showing what is the content of each of our pushbacks or phases. And additionally, we can review the content of each pushback bench before going to the next stage, generating our schedules. The scheduler is using the pushback optional extraction sequence, which is the sequence which we should follow in order to get the maximum NPV from our deposit. In addition, we are providing scheduling targets, primary and secondary. We are providing additional controls like maximum sinking rate, bench slugs between pushbacks, and this allows us to quickly generate different scheduling alternatives that are mining the pushbacks that we provide for scheduling. Just to remind you, our scheduler is optimizing all scheduling periods at the same time. So a decision that has to be made during period 5 will affect what needs to be mined in year 1, 2, 3, and 4. After the sequence is completed, the application creates a scheduler optimal extraction sequence, which is being used when generating the reports. And this is what we see on our screen, the animation of how the mining activities progress. The reports show what we have on each pushback bench and in which period this pushback bench is being mined. As part of the scheduler, we can compute our haulage requirements. I will spend a little bit time to explain how the haulage computations are carried out within NPV Scheduler. The haulage route is divided into 4 optional segments. The first one is from the block to the bench exit point. This segment is computing the time that it takes for the material to travel from the block center to the bench exit. The application knows the coordinates of each block. We are providing the bench exit coordinates, so it knows how much is the straight distance. Then we are providing a factor to take into account the extra distance or the difference in the speed. So NPV Scheduler can compute how long it takes to reach the bench exit. The next segment is the ramp. The users define the ramp gradient, up ramp and down ramp speed, and knowing the peak exit elevation, the application can compute how long it takes for the material to travel on the track up and down the ramp from the particular bench to the exit point. Next segment is the surface haul, where users define directly the time that it takes for the truck to deliver the material to each destination and how long it takes to come back empty to the pit. The fourth segment is optional. It applies to all such destinations where additional time is required for every certain amount of tons delivered to the destination. This, for example, stockpiles, leach pads, or waste dumps. This extra haulage is not available within destinations for example, like the crushers. The haulage computations are designed to work on both single and multi-mine studies, and we can quickly evaluate different strategies for using different truck fleets. And I allows us to work in two different directions to find out how many truck units we need to move certain amount of tons, and also how many tons we can move if we have certain fleet size. What we have added in the last version of NPV Scheduler, we can compute the time that is required for the material to go to and come from stockpiles. This is the interface that is introduced. It is quite similar to what we had in the previous versions, but now we can define the haulage parameters for our stockpile destinations, and they can be different from the truck fleet that can be used to move the material from the mine to the stockpiles and the other destinations. So here is where we define this truck fleet. Here we see the list of all haulage destinations, and so we can define the parameters, what is happening within each destination. Here is, for example, one of our dumps. What is new? We have added ability to provide start after period. For example, in this case, my dump A can be only accessible after period 5. So starting from year 6, our truck fleet can deliver waste to this destination, and you can see here which of the rock types are accepted at this destination. What we have added also is ability to define exit bench and travel time to the destination for each of the pushbacks. Now users can select each of the pushbacks. For example, we have here pushback 2, and I define that it takes 5 minutes for our trucks to reach the waste dump from the pit exit, and 4.5 minutes to come back empty. And also I can define the elevation at which our ramps are exiting the pit when delivering the material to our waste dump A. Just to remind you, where in the interface we can define the truck definition to be our main target. For example, I have selected that with I want to generate a schedule that shows me how many tons I can move if I have 42,000 truck hours available for all periods, but the first one, in the first period, I have only 90% of this value available. We have added quite a few new functions in our material allocation optimizer module. Just a few words about it. It's using linear programming to compute the best destination to deliver our material from different sources. Sources can be pits, one or more pits, can be existing stockpiles or external sources, material that comes somewhere outside of our deposit, for example, underground mines or some other sources if we are able to purchase extra material. The material allocation optimizer is comparing the value of the material coming from all these different sources, and it's comparing this against the capacities of all destinations, and it's sending the material to the best destination, the one that will generate the highest net value. So it compares the cost of handling if you're going to get this from a stockpile, the cost of purchasing if you're going to get this from external source, and it's comparing the recoveries and the processing costs. If the material cannot go to any of these destinations, it is wasted. What we have added within the material allocation optimizer is the ability to stockpile only reclaimable material. In the past, the users needed to manually select the the cutoff grade of the material that can be accepted to different stockpiles, which is both time-consuming and it's probably inaccurate in many situations. So now with this function implemented, the application will check and compare the rehandling cost and the value of the material that is being placed on the stockpile at the period where the material is being mined. And if the rehandling cost is high, it doesn't pay for the processing cost, the material is not stockpiled. You need to be careful when applying this option in cases where you want to use stockpiles for blending. That's why this a check mark to allow you to use this or not, depending on the situation. In most cases, you would like to have this check in place, so you don't stockpile low-grade material. The reason to need this is the fact that the material is classified as O as long as the revenue exceeds the rehabilitation cost, excluding the mining cost. However, when we are reclaiming material from our stockpiles, we have to pay the rehandling cost, and this may render significant amount of our material that is leaving the pit. It may be not profitable once it is stockpiled. In some deposits, there are quite a few million tons of material that doesn't pay for the rehandling cost, but it can be processed as a profit if it's sent directly to the processing destination. Next new function we added is the ability to define processing costs and recoveries for stockpiles defined as rock type 2. Stockpiles of type 2 stockpiles that accept multiple rock types or external sources. Until now, we had to pick a fixed value for the processing cost per ton and a recovery for each of our products. But now in this version, we can define this formula in the same way we're defining the formulas for the economic settings. My favorite part of the new functions is hiding here under Global tab. Here we can see that we have quite a few options to generate various targets. And what we see here in this case is our targets for iron ore grade, silica grade, aluminum grade, and so on. It used to be very time-consuming to generate these targets because we need to create the input variables and then defining each of the target ranges. Now, with just one press of a button, NPV Scheduler will create each of these target definitions. For example, if I select silica from the drop-down list and click Generate Target, the second target will be created, and before that it will generate automatically all the required variables. What I need to do only is to define what is the minimum and maximum range for my target. In the same fashion, you can select each of the remaining products or detailed elements and define their targets. For some special type of deposits, like cement, for example, we can quickly generate the lime saturation factor, silica modulus, and alumina modulus targets. They are quite involving to create if done manually, but now we have process to quickly generate those. I would like to spend some time and tell you about the flexible material scheduler. This is alternative scheduling algorithm that we have added to our solution about a year ago. But so far I have seen very little use of it, and I want to explain you some of the benefits of it and how it can be used in your project. Just like our conventional scheduler, it can schedule pushbacks that are created within the application, or we can schedule pushbacks that we import from external sources. The difference between the first difference between the flexible material scheduler and our conventional scheduler is the fact that the flexible material scheduler, I'm going to call it FMS, it's allowing us to stockpile material during scheduling. The setup for the flexible material scheduler is very similar to the one that we have for material allocation optimizer or for the mine flow optimizer. Actually, we're using the same setup, but the flexible material scheduler doesn't use the scheduling sequence. It is a scheduler on its own. It is creating a sequence of extracting the pushback benches depending on our targets and depending on our constraints. We have different constraints that we can define here. For example, we can define our minimum and maximum mining rates. And because it's a scheduler, we need to have a few pushback controls. What we see here on the right-hand side is the user interface, which allows us to define the constraints for each of the pushbacks. In this project, I have 8 pushbacks, and for my 6 pushbacks, I want to apply maximum sinking rate of 6. And I can only optionally select which benches should be counted towards this sinking rate limit. For example, I have selected here that only benches that have more than 50,000 tons should count towards this bench limit of 6. Also, I can define start after period for the pushback. That means this pushback cannot be mined until year 3. That's a quick way to define all these settings for the remaining pushbacks, particularly if you want to have the same sinking rate applying to all the pushbacks. The flexible material scheduler works with multi-mine projects as well, in which case you'll be able to select the mine and define the pushback settings for each of the mines in our deposit. The flexible material scheduler is a myopic optimizer. It's optimizing the schedule and the destinations one period at a time. To address this, we have an option to use the conventional scheduler as a guidance when generating schedules with FMS. What you see here is I have selected this option, and for FMS I allowed to consider only these blocks that are being considered from the conventional scheduler to be mined only up to 3 years from the current period. For example, if I'm scheduling now period 2 or year 2, I'm allowing FMS to look and make the sequence only within the blocks that have been mined in the first 5 years using our conventional scheduler. Then we have additional controls, how many benches to include in one scheduling activity and how long to run this. The flexible material scheduler is using a linear programming, mixed integer programming solver, which can be quite slow in some circumstances. That's why we have now option to define how long to compute before it produces a solution for us. and present the results. And this is the end of the new function that I wanted to present to you, and I'll be willing to answer your questions if you have any.
Perfect. With that, we'll begin the question and answer session. As I mentioned earlier, if you have any question for our presenter Damien, please type it into the chat box on your screen. And during the presentation, I have received a couple of questions. One of them being, can we determine diluted grade in NPV Scheduler? And if we can, how can we do that?
In NPV Scheduler directly works with the in situ grade. Usually we're defining the mining recovery and mining dilution globally for all blocks. And this mining dilution and mining recovery is applied to the blocks that are being processed by increasing the processing cost because of the dilution and decreasing the amount of recovered metal because of the mining recovery. So this is intended to correctly compute the block value. For all other operations, NPV Scheduler is assuming the in situ tons and grades. There's an option to report the diluted ore tonnage and waste tonnage, but for the grades, this formula needs to be defined manually by the user. So in the report option, the user can define a formula that corresponds to the dilution recovery. And in addition to the in situ grade, they can see in the report the diluted grade as well.
Perfect. Thank you, Damien. Another question we have, could we use NPVS in dimensional stone mines?
Yes, you can use NPV Scheduler in dimensional stone mines if there's a way to express what is the value of 1 ton of material within this quarry. Yes.
Perfect. Another question is, how accurate is the haulage computation in NPV Scheduler?
The haulage computations have been checked quite a few times by our customers and independently by us. A recent example showed that one of our customers has completed study on a deposit that was also completed with Komatsu, their track fleet management application, and the results came within less than 5% difference. Also, the users can export the haulage computation results from the application. In the result model for each of the subcells, they will be able to see the distance by mass variable. And this can be compared manually against a computation in Excel, and they can confirm for themselves if the computations are correct.
Perfect. Another question, Damien, can FMS schedule underground ore with open pit?
FMS can schedule anything that is defined in the input settings. And yes, we can define the underground sources as external source, and it can be used by both MAO, MFO, and the flexible material schedule. I forgot to mention you that we have added a new function a couple of versions ago that allows to define the external source such as material that comes with different tonnage and different grades in time. Because in what happens in the practice, every year we get different tonnage and different grades from our underground mines. So we need to define this for each of the periods. And yes, FMS can schedule this like scheduling all other sources that are available. FMS is not doesn't require having a schedule sequence generated like our material allocation and mine flow optimizer. The flexible material scheduler is a scheduler by itself.
Perfect. One last question, I believe. In which deposit you should use conventional scheduler, and in which deposit you should use flexible material scheduler, FMS?
It is difficult to define what type of deposit you have to use one or the other. It's a different scheduling algorithm that may work better or not for different deposits. That's why we have provided it within our solutions, so our customers, engineers can compute schedule using both algorithms and decide which one is producing better results. I want to repeat that our conventional scheduler is scheduling and optimizing the sequence for all periods at the same time. However, it doesn't consider stockpiles. While the flexible material schedule can use stockpile destinations, but it's a myopic optimizer that is scheduling period by period. So in some situations, I'm sure if you try the flexible material scheduler, you will end up in solutions only up to certain periods, which you will not end up with using our conventional scheduler. However, to allow you to avoid such situations, as I mentioned earlier, you can optionally use this control to guide the flexible material scheduler with the sequence generated from our original schedule. So to make the short question answer quickly, I'll suggest you apply both schedulers and see which one is working better for you. There is no recipe that can be applied as a general rule.
Perfect. Well, okay. Well, thank you again, Damien, and everyone who joined us today. We appreciate your time, and don't forget to join us in 2 weeks as we'll be discussing new features of our Studio 5DP software Underground. Lastly, I will be following up with an email containing a link to this recording. If you have any questions or comments, I can be reached by email at puya.tavasian@dataminesoftware.com or by phone at 604-362-1213. That's it, everyone. Hope to see you next time, and take care. Bye-bye.
Thank you. Please stand by.